Hi everyone, my name is Jingge Zhu. Today I would like to talk about semi-supervised learning. In the setting of classical supervised learning, we are given labeled data of our training data, which consists of feature vector x and corresponding label y. In the setting of semi-supervised learning, in addition to those labeled data, we have some unlabeled data, which I denote as tilde x. In both cases, we would like to train a predictor w out of this training data that for a new feature vector x, we would like to predict its corresponding label y. Given a loss function, the goal could be, for example, to minimize the access risk, where the first term is the expected loss with respect to trained hypothesis w, and the second term is the optimal expected loss. The question we ask is it possible to take advantage of those additional relatively inexpensive unlabeled data to, for example, reduce the access risk? And if yes, how could we do that? To give you some intuition as why unlabeled data could be useful, let us consider the simple example where at first we have two labeled data, this data labeled as 1 and this data labeled as 2. To find a classifier in this case, there's not much I can do but draw a threshold between those two data points. If we are given some unlabeled data, those unlabeled balls, I would probably think those balls belong to one class and those other balls belong to another class, and it seems reasonable to shift this threshold a little bit to the new one. There are many semi-supervised learning algorithms. Here is an incomplete list of them. But on the other hand, there are relatively few theoretical guarantees of semi-supervised learning algorithms as of why and under what conditions those unlabeled data are helpful. In this work, we show that for a certain generative model, unlabeled data is provably as useful as labeled data in terms of learning rate. By learning rate, we mean the convergence rate of access risk with respect to the number of data points. To set the stage, we assume that we have labeled data, n of them, distributed according to a probability model p theta of xy, and we have additional unlabeled data. In this parameterized model, we assume that the true parameter theta is unknown, except that it comes from a set, lambda. The goal is to predict y prime given x prime, and of course, those training data. We will define loss function. To give you an example, suppose that the label is from the set 0 and 1. For example, in a classification problem, the predict label could be also in this set, and we can use a 0-1 loss. But we could also choose a different prediction. For example, we could choose the prediction y hat prime to be the distribution on the set 0 and 1. For example, a Bernoulli 1/3 distribution. In this case, the hat y prime is actually a function. In this case, for example, if y prime is equal to 1, the loss would be a log 3. If y prime is equal to 0, the loss would be log of 3/2. And this loss is known as log loss or self-information loss. Again, we're interested in the access risk. And we would like to know for the two different cases, semi-supervised learning and supervised learning, how the optimal access risk scales with the number of data points, and hopefully the second case where our hypotheses depend on both unlabeled and labeled data would be better. I would like to talk about learning algorithm used in this paper. So instead of using a classical ERM algorithm, we use what we call a mixture strategy. I'm not going to the detail of this, just to mention that for log loss, this is actually equivalent to the exponential weighting or exponential weight method commonly used in online learning. To prove our theorem, we have two key assumptions. The first one is the two density functions are twice continuous differentiable with respect to theta. In other words, we are considering theta as a continuous variable. And secondly, the Fisher information matrices of those two distributions, where I denote yxy and ix, are positive definite. So this is our main theorem under the above conditions, and first assume log loss and d equals 1. Please see the paper for more general d and loss functions. For the semi-supervised learning, we have the following results. Recall that n is the number of labeled data and m is the number of unlabeled data. In the case when m equals alpha n, the access risk of semi-supervised learning is upper bound by k1 divided by 2m. And if we do not have unlabeled data, the access risk is upper bounded by k2 divided by 2m, where k2 is larger than k1. In other words, in this case, the convergence rate is the same, it's 1 over m. The benefit of the unlabeled data is reflected in this constant. We have a smaller constant here. In the semi-supervised learning case, when we have many labeled, many unlabeled data, m in the case when m is n to the 1 plus gamma for some positive gamma, in this case we have a fast convergence rate. So the access risk scales as 1 over n to the 1 plus gamma, and the loss due to the unlabeled data is reflected in the constant. So we have, if you compare case 2 and case 3, we see that the constant k3 is worse than the constant k2, but the convergence rate is faster. To give you an example, we consider the mixture model where we first sample the class 1 or 2 with probability theta and 1 minus theta. When we have the class, we will sample a feature from those two density functions. In this case, we can calculate those feature information matrices explicitly. In this case, they are scalars, and we show that semi-supervised learning, we have the convergence rate of 1 over 3m. In semi-supervised learning, when m is alpha n, we have a slightly faster convergence rate, 1 over 3m plus m, so the m shows here. And when we have many unlabeled data, the convergence rate is faster. That's 1 over n to the 1 plus gamma. So to summarize, for certain generative model, we prove that unlabeled data is equally useful, extending previous results on mixture model. We feel that some techniques are useful for related learning problems. As an organizer of Information Theory Symposium, I would like to invite you all to the largest conference in information theory held next year in Melbourne. Thank you very much.